Okay, so we're continuing our work on vectors, and we did the basics last week, I guess, didn't we? In terms of defining what a vector was, some basic sort of arithmetic, and just moving around vectors, getting used to representing different lines using known vectors, etc., etc. Okay, so we're going to kick things off this week with looking at the magnitude of a vector. So if we define our vector v as v1, v2 subscript, then the magnitude, I highly recommend watching these videos in 1.25 or 1.5 as well, and then just slowing it down as you want things a little more clearly explained, perhaps. Then the magnitude of v is given by. So this is just this is not going to be difficult, is it? We're just clarifying some things. We don't want to miss anything. So this is how we denote the magnitude of v. All right, remember the magnitude is just the length, magnitude of v, the v vector. Okay, so that guy, the magnitude of v is going to be just the square root of v1 squared plus v2 squared. So, right, nice little example would be if v is equal to 3, 4, then the magnitude of v is equal to 3 squared plus 4 squared, which is square root of 25, which is 5. Okay, no big deal there. There's another example, perhaps. I'm pulling this out of the book. All right, if we've got if v equals what's this one? 6k, and what we need to know what the magnitude is, don't we? For this, magnitude is 10. Then we would need to find k, and we would do so by saying that therefore this guy is the square root of 6 squared plus k squared, and that's equal to 10. So therefore 36 plus k squared is equal to 100, squaring both sides, and therefore k squared is equal to 64, and therefore k could be plus or minus 8. Okay, so far so good. Excellent. Let's have a look at another example. All right, let's do these examples together. So we've got these 2 points here, these two position vectors, A, 3, 5, and B. Oh, I've written them in different formats, haven't I? My apologies. This should read 3, 5. So just so we know, A is a point and B is a point. This is like coordinate geometry, isn't it? So we can think of them as points on the plane. So finding AB is finding the vector that goes from A to B. So that for us means that we go, okay, so what am I doing? I'm going from A to B. So there's two ways of looking at this. I'd like to just go, so how do I get from 3 to -1? Well, I've gone down by 4. How do I get from 5 to 3? I've gone down by 2. You could write it in a different way as B minus A. B minus B minus A, like so. You're going to get the same thing. So there's AB, righto. Now over here, look, if P X Y, so I've brought another point into the play. We're in 2 dimensions here, and AP is equal to BP. So this is distance AP equals distance BP. Sounds like P is a midpoint, but it's more than that, isn't it? If you've got 2 points on a plane, so let's just, you don't need to copy this down, I'm just giving us an idea here. So A is up here at 3, 5, and B's down here at -1, 3, say somewhere around here, -1, 3. Then we're looking at a point XY that makes the distance AP and BP the same. So if if AP were joined, and then this is AB here, -4, -2, which kind of makes sense, doesn't it? That's that vector there. Right, that vector there is AB that we just found. Now the point P has to be equidistant, doesn't it? So it would be the midpoint P, but it's not just the midpoint, is it? No, there's other points where we could plot point, say here, that's equidistant, so that AB and AP and BP are equal. And in fact, you know, we can stretch this out and find more points out here where, so P could be any of these points here. So presumably P is going to be it's going to be a variable point, and it's going to be a point expressed in algebra. And it'll be interesting to see what we get. So let's proceed. So we just need to come up with an AP, which is we're going from A to P. So we're taking X and subtracting 3, we're taking Y and subtracting 5. So that's AP. And BP, what's it doing? It's starting at B and ending up at P. So it's X minus 1, so X plus 1. And Y minus 3, so it's doing that. Now we need to make these equal to each other. So therefore, or the distances, sorry. So this is, okay. I should have just taken those away, shouldn't I? So this is just the vector, my apologies, AP, and that's the vector BP. So therefore, right, the magnitude of AP is going to be this square root of X minus 3 all squared plus Y minus 5 all squared, and the magnitude of BP is going to be this. All right, not a bad idea. Maybe if you just want to press pause and do this and then come back, it's up to you. I'll continue. So I'm now going to say that therefore I want these two to be equal to each other. I'm going to square both sides immediately so I can cut to the chase and expand. So I'm going to go x squared minus 6x plus 9 plus y squared minus 10y plus 25. I don't know if you need the commentary as I work, but there you go. You're getting me kind of thinking aloud. I don't know if that's helpful. X squared plus 2x plus 1 plus y squared minus 6y plus 9. This monster. Okay, there's going to be some cancelling going on here. I've got an x squared and an x squared. I've got a y squared and a y squared. I think that's about it. So I get negative 6x minus 10y plus 34 equaling 2x minus 6y plus 10. All right, so therefore, let's check this out. I get, I'm going to put all my x's on one side and my y's perhaps as well. 8x plus 4y minus 24 equals 0. Looks about right. Divide through by 4. I get 2x plus y is equal to 6. And in terms of y on its own, y equals 6 minus 2x. So therefore, we can say that therefore P has coordinates x 6 minus 2x. All right, now this is the, so P has this relationship here, that y is equal to 6 minus 2x. And if you think about the collection of these points here, P, so that the points are always equidistant from A and B, then it's going to be this straight line here that actually is the perpendicular bisector of AB. And I guess that's the proof thereof. So if we found AB, we have actually you find the gradient here of AB. If you think about that being x, and that's across, and so that's laterally, and this is vertically. Rise over run here is -2 over -4. So our gradient, if you like. All right, so our gradient of AB is equal to, it's a positive gradient, isn't it, of 2 over 4, or 1/2. All right, because this is right, this is run, and this is rise. Okay, so gradient of AB is a half. That means that my perpendicular gradient, so the perpendicular gradient is equal to -2. So that means that my red line here should have a -2 gradient, which we can see from y equals 6 minus 2x, sure does. Goes through the midpoint of 3, 5 and -1, 3. So the midpoint, you can work that out as well. That's, what's that? So the midpoint would be 1. And what's that for? 1, 4. So if you worked out from that information, y minus y1 is equal to -2, x minus x1, and we made y the subject, you'd have -2x, that's plus 2, add the 4 as well, and you get plus 6, -2x plus 6. All right, so here, just using a bit of coordinate geometry, what we already know, over here using what we've been talking about with vectors, arriving at, reassuringly, the same result there. Okay, so none of what we've done so far actually is, there are no questions on any of that in exercise 11E. So we need to do a little bit more work in order to be able to access those questions, get some practice in. So we're going to look at now unit and collinear vectors in the plane meaning in 2 dimensions. Okay, so we've talked, have we? I don't know, about unit vectors. A unit vector is simply a vector of length 1 unit, right? So a unit vector, I'll pause while I write. Right, so a unit vector is a vector of length 1 unit. That's all the unit vector means, unit, 1 unit. So just a point here, we've met the unit vectors horizontally and vertically, those unit vectors I and j that we've used in order to be able to write our vectors as a linear combination of our horizontal and vertical unit vectors. And now, so what we're now going to consider now is unit vectors in any direction. Okay, so let's have a look at an example. All right, so let's find a unit vector in the direction of this vector here, 3, 4. This is v, right? So we'll name this guy v. There he is. Nice bold v. Now the unit vector in the direction of v, 3, 4. So the first thing we need to figure out, right, and you can probably do this, and maybe this is a pause do play for you right now. Go and figure this. Go and figure out what the vector is that is in this direction. Right? So sorry, I haven't put the direction on there. It's going this way, isn't it? So it's got to be going in that direction. Right? It's not just parallel to it. It's going in that direction. But it's only going 1 unit. Okay, so go ahead and do that. Okay, so this vector, v, the distance, the magnitude of it, is, well, it's 3 squared plus 4 squared. I think we all know what we're doing here. 3 squared plus 4 squared, which is 5. Okay, so that whole red line goes 5 units. I only want one of those units. All right, so I just want the first of those units. Maybe I'll just chop it off there if that's 1 unit. All right, so what's that vector there worth? Well, it's going to be 1/5 of, in that direction, 3, 4, isn't it? So what the notation we use here for this vector is just a little, just this little hat sitting on, which is a bit weird. Actually looks like I'm just mirroring v in itself. But you know, if we had unit vector p would be like this, or unit vector r like this. Okay, so that's how we denote the unit vector. So the unit vector will be 1/5 in the direction of 3, 4. So we would write it, usually you'd push that 1/5 through. So you'd write it as 3/5, 4/5. So that hopefully makes sense, in that if you think about it, that's heading off in this direction. So 3/5 across and 4/5 up, so it's still going in that direction. But importantly, the magnitude is 1. Now that we could have picked, we could have taken a chunk anywhere out of here that's just 1 unit in length, and obviously that is the same vector right there. Okay, so let's have a look at let's have a look at maybe generalizing here. So if we wanted to say, well, generally, I'm picking a color. All right, so generally, all right, I'll pause. Okay, so let's do this together. Generally, so for a vector that's defined as, v1, v2, and so we're generalizing, we would say that the unit vector in the direction of v, the vector v, is, now how would we write this? So we want to go, it's 1 over the magnitude, isn't it? So we would say that, okay, it's unit vector v will be equal to 1 over the magnitude of v times v itself. All right, now you can write v itself as v1, v2, and you can get the magnitude. It would have a pretty ugly old formula actually, but that is certainly amply sufficient for our generalizations at the moment. Okay, excellent. Let's have a look at another example. We're going to bring in this collinear concept now, and then I'm going to set you to work on exercise 11E. Okay, so collinear vectors. Let's just chat for a moment about those. So they're two vectors. You might have come across this collinear term before. It just means collinear, collinear, lying on the same line. All right, together on the same line, linear. So that means that points would have come across before, perhaps, that 3 points are collinear if they're arranged on the same line. So vectors are collinear if those vectors lie on the same line. So there's an example here. In purple, I've got a u vector shooting off up and left, and the v vector here, this black vector, well, it's lying on the same vector as u. It's going in the other direction. It's got a different length, but that's all okay. It doesn't need to have the same length. It just needs to be on the same vector. It needs to be on the same line. Just have it sitting on the same line. So as ever, an example will help. Given v again, 3, 4, our old favorite. Find all possible collinear vectors with magnitude 2. Okay, so what are we talking about here? A magnitude 2 vector that not just goes in the same direction as v, although v, I need to put an arrow on him so that we know which way he's going. Doesn't need to go in the same direction. He just needs to lie on v, and he needs to be 2 in length. Now we know that v itself is 5, so it needs to be 2/5 of v's length. Okay, so I might have a vector that just does this, right? Just goes along, it gives about distance 2, and just does that. Or it could go in the other direction, right? It doesn't matter. It's bidirectional, this one. Collinear vectors can be going either way. So what are these vectors? How do we define them? What do we call them? Well, they've got length 2. So we know how to find the unit vector. I know how to find my unit vector. It's v. We found it in the previous question. It was 1/5 by 3/4, wasn't it? But that's the unit vector in the direction of v. Now we're not so worried about that. Now we're not actually looking for the unit vector in the direction of v. We want a vector of magnitude 2 in either direction. So let's give this a name. We might want to say that so let u be a collinear vector to v of magnitude 2. So therefore, what can we say about u? So u can be going in the same direction as v, and it'll be twice this unit vector, won't it? So it'll be 2/5, 3/4, 3/4, or u could be going in the other direction. Could be minus 2/5, 3/4. So you can see there that that's okay. We would rewrite these as single vectors. So that would be 3 times 2/5 would be 6/5, and 4 times 2/5 is 8/5. Or u is equal to, and in this case we just got the negative versions of what we just came up with. And so there we have examples of, so you can, there's these little vectors I drew on here. They would be, the one going in the v direction would be 6/5, 8/5. There'd be that vector. And -6/5, -8/5 would be the one going in the opposite direction to v. Okay, I reckon now we're probably reasonably well equipped so that we can have a go at exercise 11E. And I think we'll do the questions. I think we'll go questions 1 through to 6 of exercise 11E. All right, see you soon.